Let us start with the concept of algebraic equations. What are algebraic equations? If you have a polynomial, we will start with polynomial. And you know the polynomial we are doing only. This theory of equation is basically on algebraic equations. Later on, we can use calculus for trigonometric other transcendental equations also. Right now, we will be discussing which is based on algebraic equations, which are nothing but polynomial equations. Okay? So, what is an algebraic equation? Let us know it first. Algebraic equation. Let fx be a polynomial. You all have very good idea about polynomial, I hope. Let fx be a polynomial of degree n. This must be greater than or equal to 1. We are not going to discuss about constant polynomial now, because theory of equation means you have to determine root. You will find that those roots are basically zeros of a polynomial. Let fx be a polynomial of degree n, which is greater than or equal to 1, and coefficients of the polynomial, coefficients of fx are all real or complex. You know, when we state that it is polynomial fx, then obviously we are considering polynomial of one variable only. This is a polynomial on variable x. Then, if we take fx equal to 0, then if fx equal to 0, then it is an algebraic equation. You have to write fx equal to 0. Polynomial you have never written equal to 0, but here we will be writing this one as fx equal to 0, because theory of equations, there must be an equation. This fx equal to 0 means the polynomial you are comparing to 0. So zeros of polynomial we have to find as roots of this equation. This is an equation, fx equal to 0. Now, degree of polynomial, degree of fx is the degree of the equation. An algebraic equation of first degree will be of the form a1x plus b1 equal to 0. a1x, b1, this is a first degree polynomial. First degree polynomial, and this equation is satisfied by x equal to what? Minus b1 by a1. By now, we will be referring minus b1 by a1. This is a root of the first degree equation. This is a root of the equation. Zeros of polynomial we have stated in case of polynomial only, but here theoretic equation there is no need to state that this is a root of the polynomial. And if you plot a graph of this polynomial, it will intersect the graph at one point only. Okay, this graph will intersect the x-axis at one point. The graph of a1x plus b1 equal to 0 intersect x-axis at a point if the ratio minus b1 by a1 is a real number. If it is a real number, then it will intersect the real axis at the point whose coordinate you can write minus b1 by a1 comma 0. So what will be an algebraic equation of second degree? Algebraic equation of second degree will be of the form a0 x square plus bx plus c equal to 0. You can write ax square plus bx plus c equal to 0. This is basically a quadratic equation. Algebraic equation of third degree will be of the form ax cube bx square cx plus d equal to 0. So, if we want to write an algebraic equation of degree n, the general form of algebraic equation of degree n we are going to write. The general form of algebraic equation of degree n we write. This is of the form a0 x to the power n, a1 x to the power n minus 1, a2 x to the power n minus 2, this way plus an equal to 0. These coefficients a0, a1, a2 and an, they are real or complex. May be real, may be complex. All may be real, all may be complex also. Some of them may be real, some of them may be complex. It's like that. So, general form of algebraic equation of degree n is actually degree of that polynomial. Now, regarding an algebraic equation, fundamental theorem of classical algebra is very important. Why? Because this chapter is concerned with the roots of polynomial. So, we must know the nature of the root. But unfortunately, the theorem I am going to state now, its proof is beyond your scope. We will not be discussing the proof of this. Rest everything I will prove, but not this one. Okay? So, I will tell you it is beyond the scope of this session. Okay? But this theorem, fundamental theorem, will help you to understand the other theorems, and it's very important to determine the roots of, or to decide something about roots of polynomial equation. That's why we need to learn it. What is that? Let fx be a polynomial with coefficients real or complex, and it has degree greater than or equal to 1. The fundamental theorem of classical algebra asserts that every algebraic equation has at least one root, real or complex. If you have stated algebraic equation of the form a0x plus a1 equal to 0, its root I have just told you, it is minus a1 by a0. One root will be there and degree of the polynomial should be greater than or equal to 1. Constant polynomial equated to 0 will not give you an equation. Why? K equal to 0 is a constant polynomial, it has no root. So we have to start from greater than or equal to 1. It has a root. If it is of the form a0x square a1x plus b1 equal to 0, it will have two roots. You all have this idea. Quadratic equation, you all have studied. So you know quadratic equation has two roots. There may be real, maybe imaginary. But if coefficients are complex, then maybe one root real, one root imaginary. So I'll be taking one extra session on quadratic equation with you. Now for this quadratic equation, it will have two roots. Roots are determined by Siddharacharya equation. That I am not going to repeat. And if roots are real, once I tell you, it will intersect the axis at 2 points. Okay? If the graph of the equation you consider, then these are 2 points, it is intersecting. Means it has two roots, alpha and beta. It's like that. If the roots are real. But quadratic equation might have graph like this also. Then in that case, it will not intersect the x-axis. So roots will be complex in that case. Maybe this situation also. Root is going to be complex over there. For real root, it has to intersect the axis at least once. Okay? Now, this fundamental theorem ensures that equation has at least, algebraic equation has at least one root. Maybe real, maybe complex. But quadratic equation, you know, it has two roots. So, when we have stated the theorem, it is true for all the equations. And the concept of this theorem will help to develop the concept regarding root of an equation whose degree is n may be 2, 3, 4, whatever. That I am going to state now. So, two important theorems we will learn one by one. The first one is a polynomial equation of degree n greater than or equal to 1, which is coefficient real or imaginary, has exactly n roots. Fundamental theorem stated about the existence of root. But here, if it is of degree n, it will have n roots. It means an algebraic equation of degree n has exactly n roots, and at the same time, this is true that it cannot have more than n roots. Exactly n roots. Okay? How to prove this? This concept building class today, I will be discussing how to get all these things step by step. Whatever in my hand, that I can share with you. But the theorem, the fundamental theorem, is not in my hand to discuss here. So I just stated, I did not prove. So I am going to prove this one by remembering that fundamental theorem of algebra. Okay? At least one root. So this polynomial equation with coefficient let fx equal to 0 be a polynomial equation. Let x equal to alpha 1 is a root of fx equal to 0. It means f alpha will be 0, f alpha 1 equal to 0, and if x is a polynomial, if alpha 1 0, you can state that x minus alpha 1 is a factor of fx. And theory of polynomial, actually we have done many important things. X minus alpha 1 is a factor of fx. What does it mean? That fx you can write in this form: x minus alpha 1 into phi x, where phi x is a polynomial of degree n minus 1. Now, when we put fx equal to 0, because this is the algebraic equation, x minus alpha 1 phi x equal to 0. So, this implies that phi x equal to 0 is the algebraic equation, and by ft it has at least one root. By ft, fundamental theorem, it has a root x equal to alpha to 6. Then how can you write phi x going to be equal to x minus alpha 2 into some other function, say gx. What about gx? Gx is a polynomial of degree n minus 2. Now, what happened to that fx, what we have started with? The fx is now x minus alpha 1, x minus alpha 2 into gx. So, what you have done? You have expressed fx in terms of product of these two factors and gx, whose polynomial is n minus 2. Now, if you compare this to 0, then gx has at least one root. Let it be alpha 3 and it continues this manner. How long it will continue? This one has degree n minus 2. This one has degree 2. That's why it is degree n. N 2 plus n minus 2, that is n. Now, every time you compare this thing, that quotient to 0, you will be getting a root. How many roots you will get? Every time it is diminished by 1. Polynomial degree diminished by 1 root being added. So, all these roots will be, number will be n 2 plus n minus 2. We have considered n minus 2. This polynomial, next one, it will give one root and degree will be n minus 1, and so on. Every time reduced by 1. So, finally, we will be continuing up to n step, this way up to x minus alpha n. So, roots of the polynomial going to be exactly equal to n. Those are roots: alpha 1, alpha 2, alpha n. These are the roots of. Now, with this theorem, we are going to establish that algebraic equation of degree n cannot have more than n roots. How can we establish that? You assume that let beta be the n plus 1th root of fx equal to 0. Root means it will satisfy the equation. What is a root? Quadratic equation, if you get two roots 2 and 3, then x equal to 2 if you put, it will be satisfied. X equal to 3 if you put, it will be satisfied. We have assumed that if possible, let beta be n plus 1th root. Then fx, if you take this manner, suppose I forgot to take the coefficient, we take fx equal to, we have taken already. Fx, the polynomial, we have already taken as a0x. Here I forgot to take. a0 is the coefficient. And that a0 cannot be equal to 0 because it is a polynomial of degree n. This is not equal to 0. Let beta be the n plus 1th root. Then beta must satisfy fx equal to 0. Put beta over there. So a0 beta minus alpha 1, beta minus alpha 2, beta minus alpha n equal to 0. But here all these roots you have taken, they will be different from they all will be different from beta, or beta is different from all other roots, isn't it? Because you have considered that this is n plus 1 is root. So it will not belong to this category of n roots, alpha 1, alpha 2, alpha n. So beta is different from all roots. So one thing is clear, that beta minus alpha 1 not equal to 0, beta minus alpha 2 not equal to 0, beta minus alpha 3 not equal to 0. None of the root is going to be equal to 0. Beta minus this way, beta minus alpha n also not equal to 0. But you got this thing equal to 0. So what does this imply? None of them are equal to 0. This is not, this is not, this is not. So product 0 means a0 equal to 0. If you take a0 equal to 0, then it will not remain a polynomial of degree n, isn't it? It is polynomial of degree n since a0 not equal to 0. Okay, I forgot to put over there. a0 not equal to 0, those are real or complex. That is different issue. But a0 can never be 0. So what result you have reached here? a0 equal to 0. So this is a contradiction. This one is a contradiction. It cannot happen. Therefore, at most, there are n roots of an algebraic equation or polynomial equation of degree n. Hope you have. If two polynomials for theorem 2, neither of which is of degree higher than n, are equal for more than n values of the variable, then coefficients of like powers of the variables are equal and equality of the polynomial becomes an identity. I forgot to tell you what is identity and what's the difference between equation and identity. I think it was already stated to you by the teachers of secondary section that what is an identity. If you say that fx equal to 0 is an identity, then it will be satisfied for all values of x. If fx equal to 0 is an identity, then it is true for all values of x. Fx equal to x square minus 3x plus 2, it's a polynomial, and we are writing this as x minus 1, x minus 2. Now this thing you can consider, if you write x square minus 3x plus 2 equal to x minus 1, x minus 2, it is satisfied for any value of x. So this thing that x square minus 3x plus 2 equal to x minus 1 into x minus 2, this is going to be an identity. But if we put fx equal to x square minus 3x plus 2 equal to 0, then this is an equation. Because if you solve it, this will give you x equal to 1 and 2. So equation is satisfied by some values of x. And fundamental theorem and the theorem just we have done, it ensures that if it is of degree n values of x will satisfy it. But identity is satisfied by all values of x. Okay? Now in our theorem, if two polynomials neither of which degree higher than n are equal for more than n values of the variable. So you take two polynomials as fx and gx. Let a0 x to the power n, a1 x to the power n minus 1 plus n and gx equal to b1 x to the power n minus 1 plus bn. That a0, that ai's and bi's are real or complex. Doesn't matter. They are real or complex. Then fx equal to gx ensures that a0 equal to b0, a1 equal to b1, an equal to bn. Why? When? Under what condition? The condition is fx equal to gx. This thing is true for more than n values of x. Okay? We will apply the theorem 1 only to prove this. See how to prove this? You stated fx and gx are polynomial of same variable x, they are of same degree. Then you are saying like parts will be the same. To prove this, we start like by taking a third polynomial. Let phi x equal to fx minus gx. So this will be a0 minus b0 x to the power n, a1 minus b1 x to the power n minus 1. This way an minus bn. Fx is 0 and phi x is also 0. Okay? Fx 0, gx also 0. Now if phi x equal to fx minus gx equal to 0, then this will imply that a0 minus b0 x to the power n, a1 minus b1 x to the power n minus 1 plus n minus bn equal to 0. This is a polynomial. This is a polynomial of degree n and it has n plus 1 roots. Why? Because you said fx and gx both are satisfied by more than n. I am just assuming n plus 1. Many n plus 2 may be many things. Okay? This is a polynomial of degree n, polynomial equation of degree n, and it has n plus 1 roots. It has n plus 1 roots. It is possible. Is it possible? First tell me. Theorem 1, what we have done? If it is of degree n, then it will have maximum n roots. Isn't it? Exactly n roots. But this equation has exactly n number of roots. But you are telling that n plus 1 roots. So this is possible. This thing is possible if this is an identity. This is possible under what condition? This is possible only when those coefficients are equal to 0. I mean, it doesn't exist, then it will be a polynomial. It will be an identity type of thing. Okay? Satisfied by more than n. More than n means maybe infinitely many values. And identity is satisfied by more than n. So, in this case, this is the only possibility those coefficients are not existing. Such a situation will never arise. If it arises, then these two must be equal. So, they must be identical. Okay? Done? Now, we are going to discuss two important theorems on nature of an algebraic equation. Nature of equation means nature of root. These two theorems have a wide range of applications in theory of equations. Number 1. In an algebraic equation with real coefficient, irrational roots occur in conjugate pairs. It means, what does it mean then? If alpha plus root beta is a root, then alpha minus root beta is the other root. As you have done polynomial, all these comparison, factor theorem, remainder theorem, everything is done. I will give you the proof of one only. You read the second theorem. If an algebraic equation with real coefficient, imaginary root occur in conjugate pairs. So what does this imply? Alpha plus I beta and alpha minus I beta both will be root. If none of them occur, if alpha plus I beta don't occur, here we are taking rational coefficient, take care. We are not stating that they are all kind of coefficients, maybe real, maybe complex, no. We are not considering roots with complex coefficient right now. In coordinate equation I will be discussing a little bit, but not here. In algebraic equation with real coefficients, imaginary root occur in pairs. How to prove it? Or if alpha plus root beta is a root, then alpha minus root beta is the other root. They are all rational coefficients, a real. Okay? Let me give you the proof of number 1. You can try number 2 at home. So let us prove number 1. Let phi x equal to 0 is the algebraic equation. X minus alpha plus root beta, x minus alpha plus root beta must be a factor of the polynomial. isn't it? X minus alpha plus root beta is a factor of phi x equal to 0. Now, if x minus alpha minus root beta is also a factor of phi x equal to 0, then we can say that and alpha minus root beta are both roots of phi x equal to 0. Or you can go by this method. If you divide the polynomial by product of these two factors and no remainder is there, then it is done. You understand? Phi x equal to 0. If we can prove that, let us prove that x minus alpha minus root beta, the first factor, into x minus alpha plus root beta is a factor of phi x equal to 0 and there is no remainder when phi x is divided by their product, that is x minus alpha whole square minus root beta square. Okay? So how to prove this? That phi x completely divisible by this and no remainder is left over there. I mean phi x divisible, simply phi x divisible. You start this manner, let phi x equal to into gx plus r1x plus r2. In polynomial you have done that phi x divided by quadratic 1, then remainder will be a polynomial of degree 1 only. It's a first degree polynomial. Okay? Now this one satisfied by phi alpha plus root beta equal to 0. What does this imply? This implies r1 alpha plus root beta plus r2 equal to 0. So this implies r1 alpha plus r2 plus r1 root beta equal to 0 means 0 plus 0 root beta. We can write this manner. Now this is an identity. Compare third part and third free part. So on comparing, we get r1 alpha plus r2. This is 0 and r1 also 0. But r1 equal to 0, for r1 equal to 0, you put r1 0 there, it's coming r2 0. So you prove both r1 r2 equal to 0. So what does it mean? That phi x, when divided by product of these two factors, no remainder. Means phi x completely divisible by the product of these two. So this will ensure that alpha plus minus root beta both are roots. If one root is alpha plus root beta, the other root has to be alpha minus root beta. That's all. Now, this is the time to start a few problems based on the concept you have got so far. Let us start. We are going to solve this one, solve this one if one root is 1 plus root 3. How to? That 1 minus root 3 must be the other root. Just we have done the theorem. 1 plus root 3, that is x minus 1 plus root 3, and since 1 plus root 3 is a factor, is a root, so another root is 1 minus root 3. So this one and are factors of x4 minus 7x cube So now find their product. The product x minus 1 minus root 3, x minus 1 plus root 3, that is x minus 1 whole square minus 3, 1 minus 3 minus 2 must divide the polynomial x4 So how to get other two roots? Two roots are ensured. They have given only. So you divide the quotient you compare to 0, then it will be the quotient compared to 0 will give you two roots. Okay? So let me do the division portion and then I will share the result with you. I am going by long division, can be done the way we have done for synthetic division, that I will tell you in another class. Minus 2x minus 12. So by long division, I got the quotient here, x square minus 5x plus 6. No remainder is there. You just put 6 over there, it gets cancelled fully. Okay? No remainder is there. Long division. I have done it, I have shared with you. You do it by synthetic division or by long division, doesn't matter. Wherever you get easier for you, go for that. Now compare this will give you x minus 2, x equal to 2, 3. Therefore, 4 roots. Why 4 roots? Why 4 roots? Because by theorem 1, it is a 4th degree polynomial, it will have 4 roots. What are those roots? 4 roots are 1 plus root 3, or 1 plus minus root 3, 2 and 3. 4 roots are there. Now look at the second problem. This is given that this is given another 4th degree polynomial 1 root 1 plus 2i. So for this one, 1 plus 2i, 1 minus 2i are the roots. Then x minus 1 minus 2i, x minus 1 plus 2i, this product x minus 1 whole square minus x square minus 2x plus 5 must divide the polynomial. If it cannot divide with zero remainder, then the statement given in the sum is wrong. Again you have to go by long division. I'll be doing it and then share with you. You'll divide this fourth degree polynomial by seven x plus 5. See the long division. This you also can do. You divide by x square, then this thing, then x minus x I have taken, and then plus 1. No remainder is there. So again you need to compare the quotient over there, that x square minus x plus 1 0. This implies or 1 plus root 3i by 2, 1 minus root 3 by 2. Okay? So other two roots we have already got, 1 plus 2i these are the roots of the fourth degree polynomial. Okay? This is a very interesting question. Question came in many exams in many different forms. I have just chosen the simplest one to prove that roots of this equation are all real. How to do it? How to prove that roots are all real? If they are not real, they must be complex. And A, B, C, they are all real numbers here. Whatever, real or complex, this is going to be a cubic equation, 3 roots are there. If there are imaginary root, whatever real or complex ABC, those must occur in pair. So to prove this one real, we need to prove that no imaginary root exists. So let us go by contradiction. By contradiction, let us assume that alpha plus I beta is a root, and this assumption will ensure that alpha minus I beta has to be the other root. Root means it will satisfy the equation. So put x equal to alpha plus I beta once. This will give you one by alpha plus I beta, number one, and the other one going to be put x equal to alpha minus I beta over there. One by alpha minus I beta. Okay. Now what you will do there? You just subtract 1 minus 2. If you do that, minus minus minus, the LCM will be, I am subtracting this from this. LCM will be what? Alpha plus I beta was a root, alpha minus I beta. So this will be product of alpha minus A plus I beta, LCM I am taking when we are subtracting, into alpha minus A minus I beta. This will give you minus alpha minus I beta plus A. The same way here also. Alpha minus B, I am writing the result only because here, okay, alpha minus I beta plus alpha minus B I beta like this, and here plus B, and here I beta, there will be and this is going to be what? This is minus I beta minus I beta. Clear? Now see what is happening there. Alpha minus A, this get cancelled. And this also. This will give us alpha minus A whole square two I beta by alpha square plus beta square. Okay. Now take 2 I beta common. Take this one on left side. Oh sorry, this is alpha minus B, this will be alpha minus B. No, this is A, this is B. So this is real, alpha beta real number. Alpha minus A whole square plus beta square, alpha beta real, this is real, this is real, this is real. So imaginary number into real number equal to 0. The possibility will be this thing equal to 0. This implies beta equal to 0. What we have taken? Alpha plus minus I beta, these are two roots. Put beta equal to 0. So this part doesn't exist. This part doesn't exist. So roots cannot be imaginary over there. None of the root can be imaginary over there. Because if imaginary, they could have occurred in pairs. They don't occur in pairs. We have assumed alpha plus I beta, alpha minus I beta both are root, but they are giving beta equal to 0. This will ensure that so all roots are real of the given equation. So this was just introduction to algebraic equation or theory of equation. Next session we will be discussing multiple root concept and nature of root. That is the interval where they lie. We will learn Descartes' rules of signs. We will learn Newton's theorem. we learn Rolle's theorem also. Okay? Thank you.